pH, quantifying solution acidity. In order to understand pH and pOH, we have to first understand rules of logarithms. Like many processes in chemistry and other fields, pH and pOH both work on a logarithmic or anti-logarithmic scale. The significance of figures in logs and antilogs depends upon the decimal point location of the figure that is reported. The number of decimal places in a logarithm answer is equal to the number of significant figures in the measurement from which the logarithm was derived. For example, if I have a pressure reading of 4.0 times 10 to the 5th atmospheres, this is a 2 significant figure measurement. If I take the log of that same pressure, I get an answer of 5.60. 5.60 seems like we should cut off at the wrong point. It looks like it's 3 significant figures instead of 2. However, we have a break at the decimal point. So between the 5 and the 6th is our break for the decimal. After that break, there are 2 digits. Those 2 digits, or 2 decimal places, reflect the 2 significant figures in the original measurement. A log will give a measurement and a decimal location. Antilogs are similar. If I have a log value of 5.60, taking the antilog, which is 10 to the x, in this case 10 to the 5.60, will give me a number, in this instance 398107. I report this according to the number of significant figures based upon the log value. Since the log value has 2 decimal places, the answer to the antilog should have 2 significant figures. In this instance, 4.0 times 10 to the 5th. So antilogs and logs cancel each other out. Kw is the equilibrium constant for water. Water is amphoteric, which means it has both acidic and basic properties. Water can react with itself to form both acidic and basic components. For instance, if 2 water molecules come together, one can deprotonate the other since water is amphiprotic, able to both accept and transfer a proton. And so one water molecule will become a hydronium, and the other will become a hydroxide. The equilibrium for this process, then, is because pure water is an activity of 1, the reactant side of the equilibrium is 1, giving us an overall equilibrium expression of the concentration of the H3O plus times the concentration of the OH minus being equal to our equilibrium constant, Kc. In water, Kc is called Kw, where Kw stands for the ionization constant of water. For pure water at 25 degrees Celsius, the concentration of hydronium has been measured to be 1.0 times 10 to the negative 7 molar. Because hydronium and hydroxide are formed in equal concentration, the concentration of hydroxide must also be 1.0 times 10 to the minus 7. Plugging this into our equilibrium expression to solve for Kc, then, 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7 will give us a Kw value of 1.0 times 10 to the minus 14. This gives the Kw value constant for water at 25 degrees Celsius as 1.0 times 10 to the minus 14. Any introduction of changes to acids or bases in the system will change the concentration respectively for H3O plus or OH minus. Adding either H3O plus or OH minus will shift my reaction to the left-hand side of the equation. Taking away H3O plus or OH minus will shift it to the right-hand side. If I add H3O plus, it consumes more of the OH minus than it does of the H3O plus, increasing the overall hydronium concentration. Adding hydroxide will consume more of the hydronium than the hydroxide, increasing hydroxide concentration. Any aqueous solution, however, at 25 degrees Celsius will still have a ratio of H3O and OH minus that will be equal to the Kw at 25 degrees Celsius for a dilute solution. If we consider a system as a gradient between all hydroxide and all hydronium, for a solution that is all hydronium, we would have concentration of hydronium at 1 molar and concentration of hydroxide at 1 times 10 to the negative 14 molar. On the other side, we have all hydroxide, which would have a hydronium concentration of 1 times 10 to the negative 14 molar and a hydroxide concentration of 1 molar. Remember that any aqueous solution at 25 degrees Celsius still equals the Kw when the products are multiplied. So looking at our equilibrium expression, concentration of hydronium times concentration of hydroxide equals Kw. If I'm at the all hydronium side of the scale, then the 1 molar hydronium times the 1.0 times 10 to the negative 14 molar hydroxide will give 1.0 times 10 to the negative 14 as the Kw, which is the Kw constant, as it should be. The same is true for the right-hand side with all hydroxide, except that the numbers are reversed. 1.0 times 10 to the negative 14 is now the hydronium concentration, and 1 molar is the hydroxide concentration. In examining a relationship between the autoionization constant Kw and hydronium, we can use a derived scale that measures the concentration respectively of hydronium and hydroxide. This provides an alternative to using small molarities like 2.0 times 10 to the negative 13 molar for these concentrations. Any acidic solution will be dominant in hydronium concentration. A basic solution likewise will be dominant in hydroxide concentration. Using the abbreviation P, which stands for the negative log, we can express our hydronium and hydroxide concentrations in a logarithmic and antilogarithmic scale. This allows us to express molar concentrations in terms of the negative log, or the P value. So the negative log of a hydronium concentration would be represented as a pH, where H stands for the H plus or hydronium. The negative log of the hydroxide concentration would be a pOH, where OH stands for the OH minus or the hydroxide. We can also describe water's autoionization using this process then. If the autoionization constant of water, Kw, at 25 degrees Celsius is 1 times 10 to the negative 14, then the negative log of that constant, or the pKw, will be 14, because the negative log of 1 times 10 to the negative 14 is 14. Using this expression of Kw, we can examine a relationship between pH and pOH, where the Kw being equal to the hydronium and the hydroxide multiplied together gives us our 1 times 10 to the negative 14. The log of that entire expression then will give me the log of hydronium plus the log of hydroxide, because if I take a log of two things multiplied together, I can separate those out as additive logs, and that then in turn will be equal to the log of 1 times 10 to the negative 14. We can express this pH as a scale then. The log of the hydronium plus the log of the hydroxide equals the log of 1 times 10 to the minus 14. So if I take a negative of the entire thing, negative log of hydronium plus negative log of hydroxide equals negative log of 1 times 10 to the minus 14. The negative log of hydronium is the pH, the negative log of hydroxide is the pOH, and the negative log of 1 times 10 to the minus 14 is 14. So pH plus pOH always equals 14. For example, if I want to calculate pH and pOH of a solution that has 0.050 molar H+, or hydronium, I can solve for hydroxide concentration by using the equilibrium expression, where hydronium times hydroxide equals 1 times 10 to the minus 14, or Kw. To solve for Y, the hydroxide concentration, I simply divide Kw by the 0.050 hydronium concentration, which gives us a hydroxide concentration of 2.0 times 10 to the minus 13. Taking the negative log of both of these, the negative log of 0.050 is 1.30. The negative log of 2 times 10 to the minus 13 is 12.7. Adding these two together then gives us 14. So the pH at 1.30 plus the pOH at 12.7 gives us 14. According to autoionization, the concentration of water, or hydronium in water, is 1 times 10 to the negative 7, as is the concentration of hydroxide, since they'll be equal to each other. If I look at this scale then, once again, now let's add in pure water as the middle point in this sliding scale of hydroxide versus hydronium. Both concentrations in the middle will be 1 times 10 to the negative 7. The pH values then, for an all H3O plus, will be a negative log of the hydronium concentration at 1. Negative log of 1 is 0. At the all hydroxide side, the pH value will be the negative log of 1 times 10 to the negative 14, which is 14. For pure water in the middle, we have negative log of 1 times 10 to the negative 7, at 7. So our pH scale ranges from 0 to 14, with 7 as neutral water. The pOH scale will be the exact same, except the values will be reversed, where 0 would be the concentration at all hydroxide, and 14 would be the concentration at all hydronium in the case of POH. Indicators are substances which can determine pH in POH. We can determine either by the use of a pH meter or an indicator. A pH meter is a glass electrode which monitors hydronium concentration and conductivity, giving us a pH value. Indicators, on the other hand, tend to be colored organic complexes. The color of these complexes depends on pH. Usually these complexes are weak acids or weak bases. A universal indicator is a mix of several smaller indicators which can give a pH over a wide range versus the narrow range which is normally the case for a standard indicator. We can also use indicator paper, or what is called litmus paper. This is used by dipping the paper in a solution. The paper will change color corresponding to pH. This is different from an indicator, where an indicator will be added to the solution, changing the solution color.